Okay, last one of the unit. Let's talk about solving problems involving momentum conservation when external forces do act on the system. Okay. All right, so let's just go back to no external forces. If there are no external forces, I got a two-object system. I've got a 50-gram person and a 100-gram platform they're standing on a frictionless surface. Right now, the momentum is zero. If this person runs and jumps, since there's no outside force, the momentum beforehand equals momentum afterwards. So if this goes back at 2, this person goes forward at 4, I still end up with 0 kilogram meters per second. The momentum of the system is still the same. The center mass of the system is still right where it was. This might be moving to the left, and this guy might be moving to the right, but the center mass is right here because no outside force was applied to it, so it couldn't change its motion. But let's change that. This is no longer friction. Now there's friction. Now before the guy runs and jumps, his momentum is 0 and his center mass is here. As the person runs this way, what happens is this moves back slower. So this guy's able to move faster, farther. He has more time to do this. And what we find is that now this is going back at -1. This person's going at +5. And now I went from 0 to 150 kilograms meters per second of momentum in a positive direction. How is this possible? Well, there was an external force of friction, and if the board was moving this way, then the friction with the ground was pushing the opposite way. So basically, a force was applied to a part of the system in the positive direction, and consequently, what happened was it gained momentum in that positive direction, and the center mass of the system has moved in the positive direction because the center mass has to change. If you think about it, uh, if this has only moved 1 meter and this has moved 5 meters, well, the center mass has moved from here forward a bit because there's an external force acting on the system. All right, College Board likes to ask problems like this, so let's just look at one. Okay, so I have a rocket traveling to the right. It's powered, so there's a thrust force acting on it, and there's this 200 kilogram rock back here, and there's a cable, and there's a motor in here that's going to reel it in. All right, and so we just want to, after 4 seconds of being pulled towards the rocket by the tension force, we want to ask ourselves these questions. Okay, so let's just take each one of these in turn and take a look at it. Okay, so how much does the velocity of the system's center of mass change? Okay, so the center mass does have to change because there's an outside force acting on it, this thrust force. So the thrust force is 2,400 newtons. And we said we're just interested in 4 seconds. All right, so in 4 seconds time, that's going to change it by the total uh, the total mass of the whole system here is 1,200 kilograms. And so if I say force times time and divided by mass, I get 8 meters per second. That's how much I've changed the velocity of the center of mass of this system. All right. And so I know it's kind of hard to think of it that way, but just so the center mass, you can just take this the whole two objects and just say it's one thing. It's a center mass, and there's a force acting on it for this much time. So here's how much change I would expect in this velocity. What is the initial tension force on the cable? So before I started reeling it in, this is basically not a momentum problem. This is just a force problem. So this object has one force acting on it, a tension force. It has a mass of 200 kilograms. And I know so the first thing I got to do is figure out the acceleration of the system. Remember doing this back in our third unit here? So I'd say, well, okay, I have a total mass of 1,200 kilograms and a force of 2,400 newtons. So if I say F equals ma, I find that a is 2 meters per second. So then I'm going to go to this object here and say, okay, this 200 kilogram object is accelerated at 2 meters per second. How much force does that take? Well, the tension must have been 400 newtons before I started reeling it in. The next question is, well, how much does the momentum of the rocket change? Now, what we're told, if we look at the problem, I skipped over this, is that it says here, when it begins reeling in the rock, the tension force doubles. So I'm going to draw a free body diagram and say, well, okay, so here is my system, okay? Well, I'm sorry, here is my rocket, rather. And I have a thrust force on the rocket of 2,400 newtons this way and a tension force pulling backwards on 800 newtons. So I'm going to find the net force on the rocket. So the net force on the rocket is 24 in the positive direction minus 800 in the negative direction times 4 seconds is going to be my change in momentum. So the rocket part of the system is going to have a positive change of 6,400 momentum units, kilogram meters per second. How much does the momentum of the rock change? Well, let's just see here. So now the rock has 800 newtons of force acting on it for 4 seconds. It has a mass of, well, I'm not even asking. I just want to know what its momentum change is. So the delta of the rock has to be 3,200 kilogram meters per second. Did the change in the tension of the cable affect the momentum of the system? So in other words, this is an internal force. Internal forces do not change the momentum of the system. They cannot. So whatever the motion of the center of mass of the system is, it's not going to be changed by an internal force. That's the big takeaway for this unit. So if I look, if I sum up the total momentum change associated with the rock and the rocket ship, I get a total of 9,600. But if I just took the system as a whole and I said, well, I've got 2,400 newtons of force actually for 4 seconds on an object. I mean, just well, I just that's how much I have. How much momentum change would that be? The answer is 9,600 kilograms. So tension did not change the momentum of the system. Only the thrust of the rocket did. Now, we often are presented with problems where we have velocity versus time graphs when it comes to solving momentum problems. And so let's just look at one like this. So I can see from this the initial momentum of the system was zero, okay? And afterwards it was not, okay? So I can tell that there was no outside force because the center of mass of the system was unchanged afterwards, because I have 2 kilograms moving in the negative direction at 2, so that's -4, and I have 1 kilogram moving in the positive direction at 4, so that's also +4. So I can see that there's no um, the momentum of the system is still zero, so there's no external force. And that means the center of mass of the system didn't go anywhere. It's still right where it was. It's still right here. This object can move this way, and this object can move that way, but the center of mass isn't moving unless an external force acts on the system. And this is true even if the system is in motion. Okay, so now it's the same thing, but instead of these two cars initially being at rest, they were initially moving to the right in the positive direction of 4 meters per second. A force acts between them, and when it does, the same force is the exact same thing. It's just they were moving to start with, right? So what happens is when that force caused this one to lose 2 meters per second. So instead of going 4, it's now going 2. So 2 plus 2 is 4. And this one is now moving forward at 8. So 8 times 1, all right? And so what I find is that I still have the center mass traveling at 4 meters per second this way, and that these forces, there was no external force, so there's no change in the momentum of the system. It remains 4 meters per second times 3 kilograms. But what if there is an external force? So when there is an external force, then we get something like this. All right, so I see from this, I can use velocity divided by time to see that I increase by 4 meters per second in 4 seconds, so I'm accelerating at 1 meters per second. There is an external force acting on the system, otherwise it would not be accelerating. The purple line is just going to be the center mass of the system. Before they separated, their center mass was moving at an accelerated rate of 1 meter per second squared, and it's going to continue to do that. So I can look at that. I say, well, I'm accelerating at 1 meter per second squared, and I have a total mass of 3 kilograms. So I can use F equals ma to find out that the net force acting on the system is 3 newtons. Now, what that means is the center mass of the system is going to continue to accelerate at 1 meter per second squared. Even though these forces get applied, the system itself will continue to accelerate at the same rate that it did before the interaction between them. The interaction between these two objects, whether it's tension or normal, whatever it is, it cannot change the momentum of the system. The only thing that can change it is an outside force. And so the momentum of the system is going to continue to increase as a result of this force. Let's try this one here. I have a cannon on a frictionless surface, and then it's going to slide onto a surface that does have friction. So here's what I'm going to find. Okay, so the cannon was initially at rest. Okay, and then when the cannon fires, the cannonball does this, and the cannon does this. So I want to answer these questions. What is the mass of the cannon? How far did the cannon travel before it encountered friction? What was the magnitude and direction of the friction force? How far had the center of mass system moved at 7 seconds? And how about after 15 seconds? We can answer all of these just by looking at this graph. And you need to be prepared to do this on the AP test. So let's just take a look at this. All right, so the first question, what was the mass of the cannon? Well, the way I'm going to solve this, I'm going to say, well, I know that this is a 2 kilogram ball, and I can see afterwards it's traveling at 12, so 2 times 12, uh, 2 times 12 is 24, okay? Now, so I look here and I see the cannon's moving backwards at 2. So what I'm going to do is I can, well, one thing I can look here, I can say the cannon is 6 times as massive, right? Because it moved backwards at 2, where this moved forward at 12. So I can just look at that difference and say the cannon is 6 times as massive. So if it's 6 times, what's 6 times more massive than 2? 12 kilograms. All right, so now I want to know how far did the cannon travel before it encountered friction. So I look at the cannon is the one that's moving the negative direction. So it's the blue line here, right? And here's the interaction between the cannonball and the cannon. It was very short duration. I don't even see it reflected in my graph. Now, when there's no friction, it's going to continue to move at the same speed, and so that this momentum here and this momentum here are equal to each other, but that all changes at this moment here. So at time t equals 7 is when it changes. So I would simply integrate this area right here, and I'd get 2 seconds times 2 negative 2 meters per second. It has moved 4 meters in the negative direction. All right, what was the magnitude and direction of the friction force? So if I want to do that, here's what I can do. I can say, well, here's where the friction force is acting, right? So I can see that the friction force acted for 1, 2, 3. It acted for 4 seconds. So that's one thing I need to know. I've already established that the cannon has a 12 kilogram mass, and its velocity here was -2. That was its initial velocity, and its final velocity was 0. So I just put them into my impulse equation, and it turns out I can say, well, the force was 6 newtons in the positive direction. Well, how far had the center of mass of the system moved at time t equals 7 seconds? So I can see here there was no outside force acting on it, so it should be 0. And in fact, we can calculate this. We can say, well, I have a 2 kilogram object that traveled 2 times 12, so that's 24 meters in the positive direction. All right. And then I have a 12 kilogram object that moved 4 meters in the negative direction. And if I use my center mass equation, what I'm going to come up with is 0 meters. It hasn't moved at all. Cool. How far is the center mass of the system moved at t equals 15 seconds? Well, now t equals 15 seconds is a different matter. So what I would do is I would say, okay, how far did the cannonball displace? Well, the cannonball displaced, let's see, 5. So it went 5 is 10 times 12. So it displaced 120 meters. So in my center mass equation, I'm going to say center mass is equal to 2 kilograms times 120 meters for the cannonball. Now for the cannon, what do we have? Well, we know it's 12 kilograms. Now, what is its net displacement? Well, what I say here is I have -2 times 2. That gives me this. And I'm going to take half of this. So half of -2 times 4. So I get a total of -8. When I put that in there and solve, what I see is the center of mass has now moved to the right 10.28 meters. So an external force, in this case friction, pushed the cannonball in the positive direction and shifted the center of mass in the positive direction. Okay, now look at this one. Oof. Okay, I have a spring-loaded launch like the kind we used when we were doing two-dimensional kinematics, and it's falling to the ground. So here it is on its way down, and we use a remote control to fire it on its way down. So it's going to shoot a ball downwards, and this is going to be an internal force between them, which is going to push this upwards. So we said, so after falling for 1 second, the ball is launched, causing the launcher to momentarily stop. We want to draw the following graphs. Okay. So let's just try this. So a velocity versus time for this. So let's just look at these different graphs. So I want to do the center mass of the ball launcher system. There is an external force acting on the ball launcher system. It is gravity, and it's going to cause it to accelerate at g. And since we aren't told otherwise, we assume we're on Earth where g is 10. So what I should find is every second it's going to gain 10 meters per second in the negative direction. If I wanted to do the velocity of the launcher, well, it starts off falling this way, and I was told that at t equals 1 second it fires and it momentarily stops, but gravity is going to keep pulling and it's still going to go down at that same 10 meters per second squared. Now the ball was falling down, and now it got forced downward at a faster rate, and then it's going to continue to fall under the influence of gravity. And now I didn't ask you to do this, but if we wanted, well, it's right here. So if you took the center of mass, you'd notice the center of mass is right here. In other words, the center of mass didn't change. The launcher had more positive velocity, and the ball had more negative velocity, but the center of mass continued the same. Now, if I want to do the momentum of the ball launcher system, okay, So the momentum continues to increase as this system moves downwards, right? So as it falls, it's gaining velocity, so it's gaining momentum. What if I want to do the mechanical energy of the ball launcher system? Now, I'm not including the Earth, just the ball and the launcher. So that means that there's no potential energy here. Okay, so we got to be a little bit careful with defining our systems here. So that means as time goes by, since it's gaining velocity, it doesn't matter if it's negative velocity, it's still gaining kinetic energy. Remember, there's no negative kinetic energy. So as time goes by, it's gaining kinetic energy. And when I shoot that, I'm basically releasing some stored energy. So what's going to happen is there's going to be a net increase in the kinetic energy of this object, because what was stored spring energy is now, even though the spring's not part of my system, I've added energy, kinetic energy to the system. So it's going to jump up at that moment and continue to increase because of gravity. But if I say, what happens to the mechanical energy of the ball, launcher, spring, Earth system? So I've included everything. So right, as it's gaining kinetic energy, it's losing potential energy. As it gains kinetic energy from the launching of the spring, it loses potential spring energy. And so in that case, the mechanical energy of the system is not going to change, since I have only conservative forces, gravitation and spring, acting on a system that's defined to be ball, launcher, spring, Earth. Hey, that was kind of a long one. Thanks for watching. I appreciate it. We only have one unit to go after this, guys. You're doing great.